Let me set up the problem. I'm not being a pessimist. I'm not saying it's impossible in some vague way. I'm saying it's mathematically and physically constrained in ways that most people simply don't understand. And that's the interesting part. We can work it out ourselves. We don't have to take anyone's word for it. Let's start with something simple: distance. You see, space is really, really big. And I mean that in a way that your brain probably doesn't fully appreciate yet. The nearest star to us, not another galaxy, just the nearest star, is Proxima Centauri. It's about 424 light years away. Now, what does that mean? That means light. The fastest thing we know about the speed limit of the universe itself takes 4.24 years to reach us from that star, just to get there with a radio signal, just to get there with light. Let me give you a sense of scale. We've been exploring space with rockets for about 70 years now. Our fastest spacecraft ever, and I mean the absolute fastest, is the Parker Solar Probe. It goes about 120 miles per second. That's fast, that's incredible. But let's do the mathematics. If you traveled at 120 miles per second continuously without slowing down, it would take you 1.1 million years to reach Proxima Centauri. 1.1 million years, not a typo. Let me say that again so you really hear it. At our fastest speed right now, using our best technology, a trip to the nearest star would take longer than humanity has existed as a species. The pyramids are 5,000 years old. This trip would be 220 times longer than that. Now you might say, well, Feynman, surely we'll build better rockets. Surely technology will improve. And yes, maybe it will. But here's where mathematics comes in, and mathematics doesn't negotiate. This is where people get confused. They think that if we just work hard enough, if we throw enough money at the problem, if we're clever enough, we can solve it. But some problems aren't technological problems. They're physical problems. They're built into the structure of reality itself. You see, the speed of light isn't a limitation we imposed. It's not like a speed limit on a highway that we can break. Light is the speed of causality in the universe. It's the speed at which gravity propagates. It's the speed at which the very fabric of space-time communicates with itself. When you try to accelerate a massive object, that's any object with mass, like a spaceship, as it gets faster and faster, approaching the speed of light, something fascinating happens. Its mass increases, not just its apparent mass, but its actual resistance to acceleration increases. This comes directly from Einstein's equation E equals mc squared. But there's a more complete version that tells us about acceleration. As you accelerate an object, its energy increases, and its energy is related to its mass. The closer you get to the speed of light, the more energy you need to accelerate it further. At the speed of light itself, you would need infinite energy. Infinite. Not a lot, not a huge amount, infinite. And you can't have infinite energy because the universe doesn't work that way. This isn't a technological barrier. This isn't something we can engineer around. This is the structure of space-time itself. It's the geometry of the universe. To exceed the speed of light, you would have to violate the fundamental mathematics of relativity. You would have to change the nature of causality. You would have to allow events to happen before their causes. And then time travel becomes possible and causality falls apart. So let me ask you, do you think the universe made a mistake? Do you think physicists discovered something wrong? No. This has been tested, verified, confirmed over and over for more than 100 years. The speed of light is not a barrier we can break. It's a boundary that defines reality itself. Now, some people get clever. They say, okay, Feynman, we can't go faster than light. But what if we just go really, really fast? What if we go 90% the speed of light, 99%? And yes, you could do that, theoretically. There's no physical law that says you can't reach 99% of light speed. It would just require fantastic amounts of energy, and you'd have problems we haven't even started talking about yet. But let's do the math anyway, because the math is what matters. If you could build a spacecraft that goes 99% the speed of light, and remember, this is utterly impractical, it requires energies far beyond what any civilization could reasonably gather, it would still take you 425 years to reach Proxima Centauri. And Proxima Centauri is our nearest neighbor, 425 years. The United States hasn't even existed for that long. But here's the thing that really gets people. You'd have to decelerate when you got there. You'd have to slow down. Because if you're traveling at 99% light speed and you hit something, a dust particle, a micrometeorite, anything, the collision would be catastrophic. It would be like a bomb. A grain-sized piece of dust would release as much energy as a nuclear explosion. So you need to slow down. You need to match the speed of whatever star system you're arriving in. That's not negotiable. That means you need half your fuel just to decelerate. Some people suggest more. And where does that fuel come from? You have to carry it with you. So now your spacecraft needs to be twice as massive. And if it's twice as massive, you need more energy to accelerate it in the first place. Physics doesn't let you cheat. This is called the rocket equation. It was worked out by people like Konstantin Tsiolkovsky. And it's beautifully simple but ruthlessly honest. If you want to achieve high speeds, if you want to accelerate a big spacecraft, the mass of fuel required grows exponentially, not linearly. Exponentially. You need more fuel than you could possibly carry. Some scientists have proposed some interesting ideas. They talk about nuclear fusion drives. They talk about antimatter engines. They talk about laser sails. And these aren't bad ideas. They're actually quite clever. But let me tell you what the realistic projections are. Even with a nuclear fusion drive, CHIOM, which we haven't really perfected yet, you could get to Alpha Centauri in maybe 150 to 500 years. That's the optimistic estimate with technology we haven't even built yet. And there's another problem that people don't really think about deeply enough. When you're traveling through space, you're not traveling through a vacuum. Well, it is technically a vacuum. There's not much there. But there's something. There's the interstellar medium. There's hydrogen atoms. There's dust. There's cosmic rays. And if you're traveling at high speeds at a significant fraction of light speed, these particles become extremely dangerous. The hydrogen atoms become ionizing radiation. They can destroy your spacecraft from the inside out. They can kill your crew. They can fry your electronics. You need shielding. You need protection. But shielding is heavy, and heavier ships require more fuel. And we're back to the rocket equation problem again. The mathematics just keeps conspiring against us. Now let's talk about the biological problem, because this is crucial. Let's say, and this is a big assumption, let's say we solved the propulsion problem somehow. Let's say we built a magical rocket that could go 10% the speed of light. That's still 260 years to Proxima Centauri, 260 years. What would you do for 260 years in a spaceship? How do you keep people alive that long? People need air, they need water, they need food, they need to not go insane from being in a confined space for centuries. You'd need closed-loop life support systems that work perfectly for 260 years with no resupply from Earth. That's never been done. The International Space Station has been up there for about 20 years, and it gets regular resupplies. We've never maintained a closed ecology for more than a few months. Some people suggest hibernation. They say, okay, put everyone in suspended animation, and they'll sleep through the trip. That's science fiction. We cannot do that. We've never done it with anything bigger than a human cell. The human body is incredibly complex. Ice crystals form in your cells. Proteins denature. Metabolic processes stop. And when you try to bring them back, everything goes wrong. Maybe someday we'll figure it out, but not now, not soon. And even if we did, even if we figured out how to safely hibernate humans for 260 years, there's another problem, time dilation. You see, when you're traveling very fast relative to an observer, time actually slows down for you. This is relativity. It's real. It's been measured. It's not science fiction. If you traveled at 90% the speed of light for what feels like 100 years to you, 230 years would pass on Earth. Your civilization would change beyond recognition. The people who sent you would be long dead. Their descendants might not care about you anymore. Your mission would be obsolete. So let me ask you something. Let's think about the Fermi paradox. You know about this? It asks a simple question. The universe is enormous. It's billions of galaxies, each with billions of stars. The laws of physics are the same everywhere, so life should be common. But we don't see any aliens. We don't see any evidence of alien visitors. We don't hear any radio signals. We see nothing. Where is everybody? And some people speculate about all sorts of things. Maybe there are aliens and they're hiding from us. Maybe they're waiting. Maybe they crashed into Earth and the government covered it up. Maybe. But I'll tell you a simpler explanation. An explanation that doesn't require conspiracy or speculation. Maybe they're not here because they can't be here. Maybe the physics of the universe simply makes interstellar travel impractical. Maybe the distances are too vast. Maybe every civilization that develops technology also develops the knowledge that crossing those distances is fundamentally difficult. Think about it from an alien perspective. Let's say there's a civilization near Alpha Centauri. They're advanced. They've figured out fusion. They've got good rockets. Someone proposes, let's go to Earth. And the scientists do the math. And they realize that the nearest habitable planet, as far as they know, is 4.24 light years away. That's hundreds of thousands of years of travel at realistic speeds. And for what? They don't know that intelligent life is here. They don't know we exist. And by the time they arrive, if they send a ship today, humanity probably won't be around anymore. We might destroy ourselves. We might move on to something else. The technology might change. This is called the temporal alignment problem, and it's devastating. For two civilizations to meaningfully interact, they have to exist at the same time. They have to overlap, and they have to send messages or ships at the exact right moment. The odds of that happening, given that civilizations might only last a few thousand years and the universe is 13.8 billion years old, are not good. Now, I can hear some of you thinking, but Feynman, what about warp drives? What about wormholes? Aren't those allowed by Einstein's equations? And yes, technically, some solutions to Einstein's equations do describe wormholes. And yes, there are theoretical frameworks like the Alcubierre metric that describe warp bubbles. So are these possible? Let me be careful here. In mathematics, you can write down equations that describe all sorts of things. You can write down equations that describe perpetual motion machines. You can write down equations that describe closed time-like curves, time travel. But just because you can write it down doesn't mean it's physically real. Just because the mathematics is consistent doesn't mean nature allows it. For a wormhole to be traversable, to actually work for getting from point A to point B, you would need something called exotic matter. Matter with negative energy density. Matter that creates anti-gravity. We've never observed this. We don't know if it exists. And if it does exist, we'd need an enormous amount of it. Enough to stabilize a wormhole thousands of kilometers across. Where would you get this material? How much energy would it require? The calculations suggest we're talking about energy on the scale of, well, it's hard to even describe. More energy than a civilization could reasonably harness. And here's the thing. Even if you could create a wormhole, even if you had this magical exotic matter, you'd probably only get a one-way trip. You'd need another wormhole to come back. You'd need two of these civilization-spanning engineering projects just to visit the neighbors and come home. Some physicists, smart people, have suggested that maybe such things are forbidden by unknown physics. Maybe there's some principle we haven't discovered yet that prevents these shortcuts. Stephen Hawking suggested something called the chronology protection conjecture. The idea that the laws of physics might conspire to prevent time travel, to protect causality. Maybe there's something similar that prevents traversable wormholes. Maybe the mathematics allows them, but nature doesn't. And honestly, given everything we know about how the universe works, how elegant it is, how it prevents cheating, I would bet on that interpretation. The universe seems designed, or rather it has evolved through physical law, to prevent shortcuts. It prevents faster than light travel. It prevents time travel. It prevents paradoxes. It probably prevents wormholes too. So let's step back. Let's summarize what we actually know. We know the speed of light is a real limit. It's not a suggestion. It's the structure of space-time. We know that even approaching this speed requires fantastic amounts of energy. We know that traveling between stars at realistic speeds takes hundreds of thousands of years minimum. We know that keeping human beings alive for that duration is a problem we haven't solved and might never solve. We know that the distances involved are so vast that temporal alignment, the chance that two civilizations could coordinate a meeting, is vanishingly small. And these aren't just engineering problems. These aren't things you solve with more money or more clever engineers. These are constraints built into the universe itself. And I find that beautiful, actually. I find it remarkable that the universe is constructed this way. It keeps everything separated. It ensures that civilizations, if they arise, are fundamentally alone, each one isolated by the speed of light, by the vast distances, by the arrow of time itself. Now, some people get really upset when I say this. They say, but Feynman, you're being too negative. Humans are clever. We always find solutions. We went to the moon. And yes, we did. That's wonderful. That was a tremendous achievement. But the moon is 238,000 miles away. Proxima Centauri is 25 trillion miles away. That's not a difference in degree. It's not like going 10 times farther. It's a difference in kind. It's an incomprehensible difference. And I'm not saying we shouldn't try to explore space. I think we should. Absolutely we should. We should go to Mars. We should establish colonies there. We should build telescopes in space. We should send robotic probes to other star systems. Robots could do it. They don't need to breathe. They don't go insane. They can survive radiation. A small robotic probe could potentially reach another star system in a few centuries. That's possible. That's actually worth doing. But humans, biological humans, the way we are now, we're probably not going to visit other stars, and certainly not other galaxies. And it's not because we're not clever enough, it's because the universe is too big. It's because the laws of physics don't cooperate with our desires. You know what I think is really interesting? I think it's interesting that this is the case. I think it's interesting that the universe, for all its vastness, for all its possibilities, is constructed in such a way that intelligent beings are isolated from each other. I think that says something profound about existence. It says that each civilization, each intelligent species has to solve its own problems, has to figure out its own future, can't rely on visitors from across the stars in a way that's liberating. It means our future is our responsibility. It means we can't sit around waiting for advanced aliens to come and help us solve global warming or nuclear war or disease or any of the other problems we face. We have to solve them ourselves. And I think that's good. I think that's the right structure for a universe that has intelligent life in it. Now let me be clear about one more thing. I'm not saying that interstellar travel is absolutely forever impossible. I'm saying that based on our current understanding of physics, based on the laws of relativity and thermodynamics that have been tested and verified for more than a century, interstellar travel is so impractical that it might as well be impossible. There's always the possibility that physicists will discover something new, some principle we haven't understood yet, some aspect of nature that works differently than we think. But you have to be careful about that argument. You can't just say, well, maybe there's unknown physics that will save us. That's not science. That's hope. And hope is not a physics model. Every time we've thought there was unknown physics, we've been wrong. When physicists thought atoms were indivisible, we learned about the nucleus and electrons. When people thought the Earth was the center of the universe, we learned it wasn't. But the surprising thing, the thing that always happens, is that the new physics is usually more constrained, not less. Nature is more limited, not more permissive than we thought. So my guess, and it's just a guess based on patterns, is that if there is new physics, it's going to make interstellar travel even harder, not easier. It's probably going to impose additional constraints that we haven't thought of yet. But that's okay. That's wonderful, actually, because it means the universe has rules. It means nature is lawful. It means we can figure it out. And figuring things out, understanding how the world actually works, not how we wish it worked, that's the most exciting thing a human being can do. So here's my message to you. Enjoy the stars. Study them. Look at them at night. Know that they're vast and distant and real. Build telescopes. Send probes. Explore what we can explore. Marvel at what we see, but don't expect to go there. Don't expect to visit. The universe is constructed in such a way that those places are for us to look at, to wonder about, but not to travel to. And you know what? That's plenty. That's more than enough to keep us busy for the rest of human history. Because even though we might not reach the stars, we can understand them. We can figure out what they're made of. We can learn the laws that govern them. And that understanding, that's worth more than any journey. The universe isn't keeping us out. It's inviting us in, but only as observers, only as scientists, only as creatures smart enough to understand the rules of the game. And I think that's a pretty good deal.